All right, let's dive right into this explainer and demystify exactly how ionic species are separated at a microscopic level. If you've ever wondered how scientists can take a really complex liquid sample and selectively isolate specific, incredibly tiny charged particles out of the whole shebang, well, you are definitely in the right place. It's honestly a fascinating challenge, right? I mean, think about it. We're talking about separating charged, polar species that we can't even see as they rush through a system. We're dealing with chemical entities dissolved in a fluid, just in constant motion. So how on earth do we grab onto just the ones we actually want to measure while letting everything else just wash away? So here is our roadmap for today. We'll start with 1, Introduction to Ion Chromatography, move into 2, the principle of separation, look at 3, the counter-ion strategy, dig into 4, the mathematics of exchange, and wrap up with 5, solid phase extraction. Let's get to it.
Section 1. Introduction to Ion Chromatography. Okay, let's start by looking at the actual physical system housing these chemical reactions. In a macroscopic machine, the mobile phase, which is typically an aqueous ionic medium, is pumped through an injector where your sample is introduced. From there, it travels right into the column, through a suppressor, and finally hits a conductivity detector. Now, because these mobile phases are often highly corrosive acids or alkaline entities, these systems actually have to be built from specialized inert materials. But to really understand the core principle of how the separation happens, we actually need to bypass the pumps and detectors and zoom way, way down into that column to the microscopic level.
Moving on to Section 2, the principle of separation. Now, this right here is the core mechanism of retention. It is the absolute heart of ion chromatography. The separation of ions, or polar compounds, happens because they interact with ionic sites on the solid stationary phase as they are transported by the mobile phase. Our source material notes that this process is actually much slower than what you'd find in other forms of chromatography. But the absolute key takeaway here is that retention depends entirely on charge density. If an ion has a higher charge density, it's going to hold on tighter and be retained much longer on the stationary phase. It is fundamentally a battle of electrical attraction. Section 3. The counter-ion strategy. To really grasp how these ions move and interact during this microscopic battle, we need to picture a chemical game of musical chairs. Seriously, think of these counter-ions, designated as E-, as the players actively competing for the seats on the stationary phase. They are continuously pumped through the column in very high abundance within the mobile phase, which sets up a highly dynamic, ongoing equilibrium with the stationary phase. Let's actually see how this game of musical chairs plays out. Initially, the counter-ion, E-, is sitting in the seat. It's fixed on the stationary phase. Then the analyte we actually want to measure, let's call it A-, arrives in the mobile phase. What happens next is a series of successive reversible exchanges. A- literally bumps E- out of the seat, taking its place on the stationary phase. But remember, the mobile phase just keeps flowing, bringing more and more E-, which eventually bumps A- back into the flow. This constant reversible displacement is exactly what slows the analyte down. Finally, the elution process reverses the phenomenon entirely, washing the analyte out so it can be detected and regenerating that stationary phase with fresh E- ions for the next round. So a huge part of this is selecting the absolute best counter-ion to play the game. While an OH- species seems like a really simple, logical choice, our sources point out that hydrogenated carbonates, specifically carbonate and bicarbonate at a 0.0003 molar concentration, are actually the preferred choice. Why is that? Well, because these carbonated species are much more efficient at displacing the specific ions we want to separate. They just play the game of musical chairs better, which leads to much cleaner, more precise separations. Which brings us to Section 4, the mathematics of exchange. Now that we've visualized the game, let's look at the mathematical rules governing these chemical musical chairs. Because, let's be real, in analytical chemistry, every single interaction can be strictly quantified. This simple equation perfectly describes the reversible equilibrium happening between the mobile phase and the stationary phase. The M subscript stands for the mobile phase and the S stands for the stationary phase. You can see the counter-ion E and the analyte A literally swapping places back and forth. It is a beautifully balanced microscopic tug-of-war. And this tug-of-war is characterized mathematically by the exchange constant known as alpha. This is the mathematical representation of our selectivity. It dictates exactly how much preference the stationary phase has for one ion over the other. Alpha is calculated super simply by dividing Ka by Kb. But you're probably wondering, what exactly do those two K values represent in our system? Well, they are the specific distribution coefficients for the two competing species. They quantify exactly how each species behaves during our separation game. It's essentially a measure of how an ion distributes itself between the solid seating area of the stationary phase and the flowing liquid area of the mobile phase. By looking at the ratio of these two coefficients, we can perfectly calculate our system's overall selectivity.
Finally, Section 5, Solid Phase Extraction. Let's see what happens when we leverage this exchange phenomenon in a really specific way. Solid phase extraction relies entirely on this exact exchange mechanism, allowing polar species to be completely retained on the resin. If we have a sample with two competing ions, let's just call them X and Y, and the distribution coefficient of Y is greater than the distribution coefficient of X, then ion Y is simply going to be retained longer on the column. It's a direct macroscopic application of our microscopic distribution coefficients, determining the final winner of the retention battle.
And if we want to get incredibly precise, which of course we do, this formula shows us exactly how to calculate the distribution of our ions between the solid and liquid phases. The distribution coefficient for ion X is literally just the moles of X per gram of stationary phase divided by the moles of X per milliliter of mobile phase. It's just a perfect, neat mathematical snapshot of exactly where our ions are hanging out at any given moment during the process.
It really makes you think, doesn't it? I hope this explainer helped structure the principle of separation for you, taking you all the way from the physical pumps and columns right down to the mathematical constants of ionic displacement. Understanding how scientists manipulate charge density and counterions gives us just incredible control over the microscopic world. It really leaves you wondering about the hidden mathematical forces at play in the everyday chemistry all around us. Thanks for joining me today, and keep questioning the invisible world.